I don't know if I had a low immune system.
Alright guys, so everybody, every single person in this room right now, or leave. Okay. Let me start off. I don't think there should be too many questions. Are there any questions about anything? Okay.
I have 2 questions.
Oh.
Just on 66 and 69, but really only on 66, because I'm pretty sure I could use the answer.
In 4-9?
Yeah. I'm pretty sure I could use the answer from 66 to the answer.
Did you go to upstairs?
66? Oh. Oh, yeah. Alright, let me just talk to you. So it's a constant acceleration, right?
Yeah, constant
Acceleration is A. But what is A? What is A? It's the derivative of
derivative of position.
velocity.
Derivative of velocity.
So how do I get V? I anti-differentiate that.
That would just be.
My variable is T, right?
Yeah.
So what would this?
So if we anti-differentiate that, what that should be.
It's like the antiderivative of 3. It would be 3x. Well, AT is basically plus.
What's the rest of it? C. Oh, that's it.
Yeah.
Well, keep going. And they tell you it has initial velocity v naught.
Oh, okay.
Oh, look at that. People pay attention. This is number 66 and 4.9. Let me write it a little bigger. In 66, they tell you the acceleration is constant. But what is the acceleration? It's the derivative of the velocity. So to get the velocity, I just anti-differentiate that.
Are we officially at intervals?
No, not even. We're almost there. Almost. After today, we'll be
Isn't
there.
it like the same?
So what would how do you anti-derive A?
Plus C.
AT plus C, kick ass. And they tell you the initial velocity was V naught, V sub O. That's the notation you use for initial. Like the initial temperature would be TO, right? Or even TI sometimes, but TO is more better. It's more better. So if the initial velocity, so velocity at time 0, has to be VO, then obviously C is VO. So the velocity equation is AT plus VO. And the question is all about this, the position. So you just do exactly what we just did one more time. Right? So to get to the position, what do I have to do to the velocity?
Would that be
Anti-differentiate it.
So that would be AT squared.
Almost, except there's a problem with that.
Oh, 1/2.
Yeah, you got to put a 1/2 to kill the 2 that wants to come down, right?
And then V naught T
Plus V naught T.
plus C.
I like it. Not the same C as before, but.
Yeah.
And then they tell you the initial position, blah, 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 the barrel C's. Not too bad. It just sounds weird when you first read through it, but you got to remember, acceleration is itself a derivative of something else. So you can just do the opposite of derivative to get to where it came from. I like it. All right. Anything else from 4.9? Yes. Oh, okay. Well, I like it. So 15 tells you to graph this. They say a function where f of 0 is 0. The slope at -2 and, what's it say, 1 and 9 are all 0. So what's happening there possibly at those 3 locations? There are locations where what might be? There might be a max or min, or there could just be a place where it goes like that, right? Okay. Boy, they got a lot of stuff here. The limit as it goes to infinity is 0. I mean, and they just keep on. They list a ton of stuff here. I love it. They basically are giving you. Wait. Am I looking at the right thing? No. Whoever asked that question, you got to be. Oh, Tori. I'm looking at the review. I was going to say that is quite the problem. Okay. So Tori, you should have immediately been like, "What the hell are you doing?" And I would have been like, "Oh shit." I'm on several medications at the moment, so that'll be my excuse. So this one says, find the most general antiderivative of the function. So I'm hoping something about this function is going to jump out as remarkably obvious. I mean, the way it is, we do not have an antiderivative quotient rule. We don't. In fact, there isn't one. All right? It's too bad for us. So we have integrals, antiderivatives will always be harder than derivatives could ever hope to be. Always. Unless it's something really simple like the integral of 1 is x, Jaffier, plus c. So what's a good thing to do?
Split it up.
Yeah, so I get t negative 1/2 plus t to the 1/2 plus t to the 3/2. Is that cool? Just subtract half a t from everybody. Because you're divided by t to the 1/2, so subtract a half from all the exponents. And then you can attack this with the rule we came up with. We said if g of something, screw it, Jeff. Just if it's x to the n, what's the antiderivative of that? X to the n plus 1 over. Yeah, so just apply that here, and here, and then just tack on a plus c to cover your ass for the unknown constant that might have been there. Right? I keep becoming a Muppet. That's my thing this semester, I think. I don't know what that's all about. I can't blame that on medication. Is that all right? So I think that first step is definitely, you can't do it at all. Oh my God. So thank God we can write it like that. All right. Okay, so let's get into 5. Chapter 5. And I'm going to start in a very strange place. Makes sense because I seem to always be in a strange place. Might as well start there. Have you guys ever seen the proof of the area formula of a circle? It's very interesting. I'm going to show it to you. The reason I'm showing it to you is we're going to learn today how to find the area under a curve. So I can find the area under this. You better be able to find the area under that. If my function is 2, and I want to know the area under 2 between the x-axis from 1 to 4, what's that area going to be? 3 times 2 is 6. And, oh, wow. So calculus is like, don't even use me. What the hell? Calculus comes in when I have something, woohoo, and I want to know the area below this thing. Okay, I don't have a geometrical formula for that. Holy shit. So I'm going to do something related to what we do here. So I know you know the area formula of a circle. What is the area formula of a circle? All right. I was hoping it wasn't too big of an assumption. What's the circumference of this circle? And some of you guys realize the calculus possibly involved there. I actually pointed it out to my Math 90 students without telling them it was coming. So here's what we do. This is really kind of nifty. And someday I'll actually do this with construction paper. And as I say that, I realize they probably never will. But I did this with my Math 120 class the other day. If I take this and I cut, but I don't cut through. I cut from the center out. But I don't cut through the ends. But I do cut across like this, right? Cut across, and then I cut out, but not through the ends, then I pick it up. Can you guys imagine that? I pick it up and open it. So it looks like the top of a jack-o'-lantern's, right. All right. And now I'll do the same thing with the bottom. and then I open it and shove it in there. Right? Just pretend like you guys see what's supposed to be happening up here, right?
Yeah.
Now, obviously, it's not perfect. It's going to be like a little slanted, but can you imagine in the limit that my triangles become infinite? This would be perfect. How long is this?
Their circumference.
No. Careful. Where did it come from? So this is how long? Pi r, right? It's half the circumference. You with me? Because the other half is here. So I've made a rectangle out of the shape that I didn't know, because I know the rectangles. And what's this going to be? R. So what's the area? Shit, yeah. So when I have a shape that I don't know the area of it, I try to break it into parts that I know the area of. So that's exactly what we do with it, believe it or not. The first step in the second half of calculus is breaking up an area like this into little rectangles. If I break it up into rectangles, somebody knows where I'm going with this. Right, I want to go from A to B. What would the area be? I just add up all the areas of the rectangles. Very interesting. So, just to make sure you understand what's going on, 4-9 was anti-derivatives.
General. Yeah.
5-1 and 5-2 are finding the area under curves. Then we want to merge those two so we don't have to do this process forever, please dear God. Right? So some of you, if you ever had any calculus before, I don't know how much or how little your teacher went through this. Right? This is important to go through so you understand what integrals really are. Okay. Where am I? Okay. Let's deal with this. So let me give you the overarching idea, and then we'll try some concrete examples out. So if I have some function, A to B, and actually let's see let's see if you can handle it being non-concrete for the moment. Let's say I want to use n rectangles to get the area under here.
Okay.
So obviously if I use one rectangle, it will not be very good unless my function happens to go up and down about the same amount. I don't know if you guys understand. So I use one rectangle. So here's the idea though. If I use one rectangle, how tall will that rectangle be? I have some leeway here. So one thing you could do, you could say, if I use a rectangle, I can say the height will be determined by the left endpoint of that rectangle. So maybe the height would be that. Would that be too big or too small?
Too small.
Obviously too small. Or I could say it's the left endpoint. So then it would be this. Well, let's pretend like it's that. That would be
Too big.
So, yeah, this feels like this is related to Goldilocks somehow. This guy was just right. So one smart thing to do then is that if I did the left endpoint and the right endpoint, I could just take the average of those two. Or I could use the midpoint. Okay. So obviously I'm not going to use one big-ass rectangle, right? That's really sort of a slap in the face to the function. The function is all, look at me, I'm going to show you. That's a little, oh shit. I want to get a little better resolution on this, right? So I want to use n rectangles, however many. If I use, so what's really important here is I want to be able to calculate the areas of each rectangle so I can then add them up. So the height is going to be determined on whether I want to use left endpoints or right endpoints. You come with that? Okay. So how wide will each rectangle be? That is actually a question you can figure out right now. How wide would each rectangle be so I can fit n of them between A and B? You can do it.
X.
Huh?
You could make it as small or as big as you
No. I want to use n rectangles, a certain set number of rectangles. So watch. Let's just, all right. So I want to see how far I can push it. I pushed it too far already. Let's say it went from 1 to 4, and I want to use 6 rectangles. I want to fit 6 rectangles in between 1 and 4. How wide would each one have to be? Yes. How far do I have to go? 3. And how many steps do I want to take? 6. So each step has to be 1/2, right? So if I took one rectangle, I would go up to 1.5, right? And then 2 would be a 2, and 3 would be blah, 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 and then eventually I get 6 up to 4. You guys with me? So what's the formula then? Like Aaron said, I'm sorry, Aaron.
B minus A minus A.
So when I fit this many rectangles into this much range of numbers, right? All right, let that make sense, yes.
Is this MRAM?
I have no idea what the hell you mean.
Midpoint rectangular?
Oh,
No?
whatever your teacher was, I think that, yes, that's their own thing they made up. MRAM sounds like the company that took over for Enron. This is leading up to Riemann Sums. Is that what you mean?
Yeah. Like the L
Riemann Sums. I forget if it's I before E, to be honest, for poor Riemann.
Riemann is A over N. That's like.
All right. Guys, hey, what was that? What did that represent?
N rectangle.
The
Number.
Width?
The width.
width. What's the number of rectangles? Probably, yeah. So the width, I'm going to call it delta x, because that's how much I'm going to let x change by. So my first rectangle would go out to a plus delta x. And if I want it to be the left end point that tells me the height, it would be there. If I want it to be the right end point that tells me the height, it would be there. So let's just stick with left end point first, all right? Let's do this left end point.
Okay.
Just so I can get you to see what the formula is going to be. What's the area of this rectangle then?
A plus delta A.
A plus
F of A.
So we'll call this A1. So I'm sorry, do it again?
Delta X times F of A.
Delta x times f of a, I love it. Right? And so let me be a little more specific here. Let me call this guy x1. So here's x2. So this will actually be delta x times f of x1. So what's the next rectangle's area going to be? Delta x times f of
x2.
That's insane.
Dear God.
And then I want to add those up. All right, so let me do this. Let me transition into a concrete example. I think that'll make it easier to take the next few steps. And then we'll come back and see if we can write a general formula for what we did. Okay. So let's take an actual function, something nice. Doesn't matter, Jeff. Let's say 10 minutes. I like it. Yeah, I like it. Cool. This will work out nice. And I want to use. Oh, what's going to be okay, Jeff? Let's use. Let's not go crazy here. Let's use. Let's make this first one really, really, really almost too nice. Something new for me. So I want to estimate the area under that function. And when I say under, I don't mean the area under it would be infinite, because it doesn't stop. But the ground is the x-axis, right? So under means stopping at the x-axis. Which is weird if you have a negative function, because then you get negative area. Oh shit, let's not worry about that yet. Negative area exists. Some books are all freaked out about negative area. But the negative sign just means it's area that's below. Who cares? Like a negative velocity. Doesn't mean you're going into yourself. It just means you're going backwards. Right? Who cares? Some books freak out about it. I don't understand. Alright, so what's this thing look like roughly? At 10, it's where? I mean, at 1, it's at 10. Good job. Too many medications. So 1, it's at 10. And at 5, it's where? It's at 2, so it's roughly just a little below 2.5. Okay. So it looks like this, roughly, right? No, that's not too bad. Is that right? Because that's 1 over x looks like that, and looks like a shifted, rotated hyperbola. So I'm trying to find the area under that. So if I use, let's use, like I said over here, let's use left endpoints. How wide are my rectangles going to be? I made this exceptionally nice. Yeah. So 5 minus 1 over 4, so they're going to be a width of 1. Right? So you can go ahead and draw in the rectangles here. Right? And the height, what's the height of the first rectangle going to be, considering you're using left endpoints? Yeah, it's going to be 10. So is this going to overshoot or undershoot?
Over.
Yeah, over. So let's see, 1, 2, 3, 4, thank God. Alright, I really want you with me on this. So this is a very, and even if I made the delta, if the delta x came out to be 3/4, you should be able to handle that, right? The math isn't really going to change that much. It's going to be a little bit more discussing numbers, but we should be fine with it. So the first rectangle looks like that.
Yes.
So there exists something called like the Trapezoidal Rule, right? So you learned that actually in Math 280 for some reason. But that would just be make a trapezoid over there and it would fit better. So there are modifications to this very basic idea. How can I make this better, whatever the answer is going to be? We're going to get an answer for this. It's going to be too much, obviously. We could take right endpoints and average them out. But what's fundamentally about this problem that really makes it bad? We're only using 4 rectangles. So if I used 80 rectangles, my resolution gets much better, right? Yeah. I don't have such a wide area with the same height. The height changes more often. You get better resolution on it. I like it. So of course eventually we're going to take the limit as my number of rectangles goes to infinity, and that somehow we're going to tie into something easy, right? Eventually, someday. Right?
Someday, not today.
Alright, not today.
You like that?
So let's talk about this. So how do I say this? So this first rectangle has height f of 1, which is 10. So let's say that's h1.
Okay.
The next rectangle is going to have a height f of what? 2. So its height should be 5, and obviously it is. Are you guys kind of with me?
Yes.
So I'm gonna make this more formal, a nice little formula that we can just throw stuff into. But right now, I just want to pull it apart to its pieces. The next rectangle will be how tall?
3.
F of 3, which is 10/3, and the next rectangle, the last rectangle. Jeff, get in there. H of 4 will be 5/2. I like it. So, can you find the area of each rectangle? What's the area of the first rectangle?
10 times
And
1.
can you see? Yeah, the width is 1.
Yeah.
So can't I just, in general, I could just take all the heights. Let me see if you guys agree with me on this. If I take all the heights and multiply by the width like that, like undistribute the width, because every one of them is going to have delta x in it. The only thing that's changing is the height. So that's the kind of an improvement right there. The width is 1, that's nice. So the total area then is
15 plus
125 over 6.
15.
I don't know.
A lot.
20.2 thirds. 20.66. I don't know. Oh, I was close. 20 point. Oh, it's out of 6, Jeff. 83333. All right, you guys take a second. Do everything we just did, but do it with right endpoints. See if you can do that. Do what we just did, but do it with right endpoints. So what's going to change?
The height.
The heights of each one. Are you going to get a larger or smaller number than this?
Smaller.
Because now each one is going to underestimate. I like to do it. And then I'll show you something really cool in your calculator.
Wow.
Just so cool. Show this to you kind of early because it's such a good visual. So it's nice. Some of you guys realize you've already done a lot of work you need, right? What's the only thing missing? I don't know if anybody's realized that. I need 1 one more color. Oh, I haven't used black in there yet. Okay. So now height, rectangle 1 is going to be this tall, right? Because it's based on the right endpoint. So how tall is the last one going to be? It's going to be that. So the only thing I don't have, I hope you realize, I'm not going to use that one, right? But I am going to have another one for that last one. You guys see, we already got all the work done except for I have to throw the first one out. Why do I throw 10 out? Because it was for that, I'm not going to use that endpoint, am I? I really want you to understand. I'm going to push you a little bit because this will make your work a lot quicker. A lot of the problems ask you to find both endpoints. Well, once you've done this, you've done a lot of the work for the next step. So this is for left endpoints. So let's say for right endpoints, it'll be 5, that's this guy, right? Plus 10 thirds, plus 5 halves, plus this height is 2, because it's based on the right endpoint, 5. 10 divided by 5 is 2. So what's the area using right endpoints? Yeah, you just subtract 8 from that, 12.83. Is that right? And then what's the average of those two?
16.
That's crazy. Yeah, 16.83. All right, let me stop there for a second. And you guys see how this, and actually this would be called the area using the midpoints. Why does it equal that? Because the midpoint, well, it doesn't always equal that exactly, so let me clear. The midpoint's sort of like the average of these two, but not perfectly because it's not a straight line, right? But midpoint, if you just do midpoints, they normally will be better than left or right endpoints, whatever we'll hope to be. But let me show you this nice visual. If you have a calculator with you, you can do this with me, which is kind of nice. Probably show you your computer. I love this visual though. So the calculator costs enough money. It should be able to do some of this stuff. Ooh, look at that, nice. So if I put in here the function I'm dealing with, 10 divided by x. And I'm going to introduce a symbol. Well, let's see. I'm doing some of this earlier than normal, but oh well. I just love the visual of this. So, I'll tell you what, to make me feel a little better about this, let's develop the general formula. I'll show you where the symbol comes from, and then I'll show you how to work it in the calculator. So I got to turn you back around.
How about that?
Yes, exactly. So what did we do here to find it? We took f of x, let me just call it xi. Is that cool? Because I could be 1, 2, 3. Sure. All right, I like it. And we multiplied that by delta x. And then we added them all up. Okay, so how do I use, you've done pre-calculus, some of you guys have done statistics, especially the stats people should be familiar with this notation, but how do you represent sum? Yes. And it'll be from, if we do the, what do you want to say? Oh, it doesn't matter. It doesn't matter which one. From 1 to, well, in general. N. I like it. Because n represents the number of rectangles. I like it. Because how many entries did I have here? 4, because I had 4 rectangles. I like it. You guys with me? That is the formula for using a certain finite number of rectangles to estimate the area. The more rectangles you use, the better the estimate is. So it kind of makes sense to merge two ideas. This idea with that idea. Right? If I let my number of rectangles become infinite, then my work will take a long time. No. We'll learn some shortcuts, and then we'll learn the ultimate shortcut. But as usual, we won't learn the ultimate shortcut until later. this is really kind of nifty.
Yeah.
This I replace with a symbol that is actually exactly what it looks like. It's the letter S elongated to represent an infinite sum. I just like that idea. So it's the letter S elongated. And it represents an infinite sum of function heights as x changes. So for derivatives, for example, this is supposed to be the antiderivative, so it should have some derivative notation in it because it's working backwards. We don't say delta x when it's infinitesimally small. We call it dx, right? So this would be f of x dx. All right, from A to B. So, and that's how we represent from something to something else. It's kind of nice. It's a very compact notation. It took a long time to develop, which only makes sense. Like, how do we do that? I don't know. From another. All right. It's exactly that sound. So, this is called it is called the antiderivative, but more efficiently it's called the integral. All right. There's some details I got to fill in, and I am. Screw it, Jeff, you're fine. I just want to show you this. There's a few details to fill in. Hopefully it's pretty obvious that there's some details to fill in. So now watch this. It's kind of cool.
I'm ready.
So put the function in. Zoom 6 so we all have the same picture. So there's that. So I only want the integral from 1 to 5. So the detail we have to fill in is... Oh yeah, I got to turn you around. This is actually not always true. There are always some funky-ass functions that don't quite work. So most of the functions we look at, it'll work. We still have to prove that this idea of finding areas under curves is somehow related to the integral. And actually, what I'm forgetting. What we still need to show is it's fine. We have to show that this integral is somehow related to the antiderivative, which is not even a part of this. I'm fine. I'm sorry. I'm trying to make myself feel better about jumping over things. I haven't. All we know is I've said that this idea of finding the area, I use this symbol to mean I'm using an infinite number of rectangles. All that is actually good. The next step we're going to want to take is to marry this with antiderivatives somehow. And some of you guys, I don't know if your teacher even made a big deal of the fact that it's something you have to actually prove. It isn't just, that's it, that's the way it is. So knowing me, you know I'm going to show you some kind of proof. So that's the integral. So to check this is not going to be perfect, but this averaging should get pretty close. So now watch this. I don't know if you've noticed this, but for example, if you hit second calc, you see derivatives in here. So you can find the derivative at any point on a curve. Right? So it's really, really good idea to play with the calculator. But the next one down is integral. So if I choose number 7, watch what it asks me. What's the lower limit? Well, I want to go from 1 to 5, right? Now what? I love this visual. So it's going to use an infinite, or not infinite, but for the calculator, close to infinite. What did we get? 16.83. Using 4 rectangles, right? And what's the actual answer using an infinite number of rectangles? I'd say we did pretty good. If we used 5 rectangles, it would have gotten even closer. Obviously, right? If we used 3 rectangles, even further away. Sweet. How are we doing so far? Is that kind of cool?
That's pretty cool.
That's pretty cool, thank you. I thought so. And the visual is really kind of cool too. It sucks, you gotta redraw it to get, if you do some other stuff, it doesn't go away. So you have to redraw it to make it go away. But I can live with that trade-off. Okay. So that's a nice way to kind of check your work. It should not be the same answer, of course, because we're not using anywhere near an infinite number of rectangles. But if you do the averaging thing or use the midpoints, it should be close. It should be close. Okay, so what I want you guys to do, let me give you this here. I got a nice little function for you guys to work with.
this is on my chest. I can't tell specifically yet.
You guys, what's up? Oh, don't worry. I gave them on the way back again. Anybody doing anything interesting for Halloween? No? A friend of mine, her daughter, she's dressed up as a zombie ghost princess, and I was thinking, that's just so kick-ass. And another friend of mine, her son, wanted to be a super dinosaur. So like a dinosaur with a cape. These dinosaurs needed, I was thinking it should have been Batsaur or something. I'm Batsaur. But it sounded a little bit iffy if you think about it too much.
How'd you do it? How'd you get infected?
Yeah.